information that's useful to enhance our lives on Earth. Next slide, please. And now we've recently got a fourth. Back a slide. Yeah, Iris². So it's our fourth flagship component, recently approved by the European Council and the European Parliament. It's the infrastructure for resilience, interconnectivity, and security by satellite. There are actually a number of Iris projects, which is why this one is called Iris², just to differentiate it from the existing Iris projects. Next slide, please. So just a word about the European Commission and the partners that we work with to bring the European Union space program to Europe, but also to the globe. So there's the European Commission, which is who I work for, and we are the program managers for the European Union space program. We oversee the political and strategic objectives of the European Union space program, but we're not technical experts. So we rely on partners. So we have EUSPA, the European Union Agency for the Space Program, and they are the exploitation managers. They help us run the system on a day-to-day basis, and then essentially the interface for us with the space program. And then we have the European Space Agency, ESA. They are the design authority. They're really the technical experts who design the system in partnership with industry, and they bring the system to life, essentially. So all three of them work together, European Commission, the European Union Agency for the Space Program, and the European Space Agency. And we have a framework partnership agreement that ties all three together to oversee the operations and the implementation and the exploitation of the European Union space program. Next slide, please. So now I'm going to talk about Galileo. Thank you. So Galileo has some unique features. As I said, it's essentially our European version of GPS, but it has some unique features. The search and rescue feature, SAR, search and rescue, and then we have the search and rescue return link. That's the SAR RL. And then we have some additional new features that we are bringing online. So we have EWS, the Emergency Warning Service, OS NMA, that's the Open Service Navigation Message Authentication, and then HAS, the High Accuracy Service. Now, all of those, apart from EWS, are currently operational and so providing extra features over existing global satellite navigation systems. So I will describe each of these in the following slides. Next slide, please. So the Galileo Search and Rescue. So this is something that's been active and since 2016. Some of you may have heard of the COSPAS SARSAT system. It's an international system. It's France, the US, Canada, and Russia. And they all got together many years ago and launched an initiative to have an international distress system that could receive emergency beacon transmissions on 406 megahertz. And this system has been active for many years, but about 10 years ago, we decided that we would fit COSPAS SARSAT payloads on board our Galileo satellites. And since 2016, all Galileo satellites except two have these emergency distress beacon receivers on board, and they can pick up the messages from distress beacons when they are triggered. So a distress beacon is a device that you can buy. They're quite small, maybe just a bit bigger than a standard GPS device, and they can be triggered if you carry one and you're out on the sea, or maybe you're in a desert somewhere and you come into difficulties and you need rescuing. You can set off this beacon, and it sends out a signal on the 406 megahertz frequency, and then our satellites on Galileo will receive those distress beacon signals, and it then relays that signal back down to the coordination center on the ground, and then you can be rescued, hopefully. In the past, so before Galileo became operational, took up to 4 hours for those distress beacon signals to be received. And in fact, the position fix from those signals was around 4 kilometers. Since Galileo has become operational with its search and rescue feature, that position location is now down to under 10 minutes. And the location accuracy, and that's purely from the Doppler of the spacecraft picking up the signal, which is a requirement of the Cosmos SARSAT system. We can locate that accuracy down to under 1 kilometer, maybe even down to 500 meters. Of course, if you add the GNSS component, that takes the accuracy down to meter level. But for Cosmos SARSAT purposes, in terms of certification, they have to rely on the Doppler measurements. It has to be completely standalone from the GNSS capabilities. So that's a major improvement in terms of locating people in distress. And we know that already that it has saved lives. But there are some new features that we've incorporated into our search and rescue capability, and that's the capability to return a signal back to the distress beacon to say that the distress beacon signal has been received. And obviously, if you're in a rescue situation, it's a motivational boost to know that help is on its way. But there are even more features. So we have the ability to remotely activate beacons. If you remember the MH370 disaster where an aircraft was lost, essentially someone on the aircraft turned off all of the communication systems on the aircraft, so there was no way of knowing where the aircraft was. But actually, the beacon that controls the Cosmos SARSAT could have been activated remotely, completely separately from the aircraft internal systems. So we now have this feature. It's called remote activation of beacons, and that could be employed on future aircraft. And then we have the two-way distress communication. This would enable beacons to actually send messages to each other via the satellite links, and that could mean that a ship or something that was closer to a ship that was sinking, perhaps, could be able to reach the distressed sooner than the rescue services themselves. So that's another interesting feature. And then we have the distress position sharing. Again, the distress beacon can share its position not just to the emergency services, but to other potential rescuers in the vicinity. So that all enables rescues to take place much more quickly. Next slide, please. And this new feature, the emergency warning service, is a new feature that is coming in the next few years. So it will offer global coverage. It requires no mobile connection. So in cases where the terrestrial network is knocked out, you can still be provided with emergency warning messages via the Galileo satellites. We use spare capacity on the open service. It can be on-demand broadcast of alert messages activated through an authorized entity within particular countries. It's complementary to existing systems. It's not meant to replace terrestrial communications, but it can complement them. And it provides geolocation using an oval. So you can see there in the picture on the right-hand side, an oval, and that's the message structure defines a particular oval shape. And this is because we have a limited number of bits within the capacity of the signal, but it's sufficient to provide location of a particular area that maybe is at threat of an emergency situation. And the size of the oval can be determined by the parameters in the message. The proof of concept of this service has been demonstrated in Australia via our helpful colleagues in Japan via the QZSS satellite system. Next slide, please. And then we have the open service navigation message authentication. So the open service is the standard Galileo service. It's the position service that you'll get with a smartphone. So if you have a smartphone that was made in the last 5 years or so, there's a very high likelihood that it would have a Galileo receiver capability embedded within that, alongside GPS, GLONASS, and Beidou. You don't get to choose. Normally, the chip on your smartphone will decide which is the best combination of signals that it can provide the best position fix. But we know that Galileo is actually the most accurate GNSS signal out there at the moment. So we've added this navigation message authentication as a way of providing some level of confidence for users that the position fixes that they are getting are actually from Galileo and not from a spoofer. Spoofing, we have seen, maybe you've seen in the press, is now becoming a technical capability, technically feasible for malicious entities that want to spoof position fixes. So with this navigation message authentication, it's not 100% doesn't 100% protect you against spoofers, but it does provide some level of confidence that the signal is coming from Galileo and not from a spoofer. So we have tested this system. It's now operational. First signals were transmitted earlier this year. The chart on the lower right-hand side shows you that there's no impact on legacy users. That is those people who have receivers that maybe cannot understand the navigation message. So they're just using the basic open service signal. So that we know it has no impact on legacy users. The chart on the top right shows where the service is currently available. That will be expanded globally, but is available globally at the moment. But it really has the most let's say the most focus over Europe at the moment, but that will be expanded globally in the future. Next slide, please. And then we have the high accuracy service. So this is something we're very excited about. Current Galileo signals, the open service, as I said, is the most accurate GNSS signal out there. So you'll get an accuracy level of around 1 to 2 meters in ideal circumstances. With the high accuracy service, which provides data on a third Galileo frequency, what we call the E6 frequency, that can provide 20 centimeter level of accuracy. This is something very exciting. It's 20 centimeter level provided for free. So this is not something that you have to pay for. If your receiver is capable of receiving the third frequency, then you'll be able to get 20 centimeter level accuracy. And it's something that we hope will be rolled out in more and more receivers in the coming years. So look out for that as a feature that will be available with GNSS receivers. We've published a note, so if you are a receiver manufacturer and you wish to incorporate it into your designs, we have a full an ICD available at the web link there. So yeah, we encourage you to use it, and we think it's a very exciting thing for many applications. So next slide, please. So these are the main characteristics of the high accuracy service. Now, essentially, service level 1 and service level 2. Service level 1 is global, and then service level 2 is uh, covering the European area. So essentially, the parameters are the same. So you'll get the same accuracy, whether you are in Taiwan or whether you are in Europe. The key difference here is the convergence time. So you may have seen from an earlier slide that convergence time from low Earth orbit satellites is much faster. Because we are in medium Earth orbit, we cannot offer the same convergence time as low Earth orbit satellites. But nonetheless, we are providing convergence time on a global basis of around 300 seconds, which is it's about 5 minutes, or is 5 minutes. That's Still quite a good convergence time in comparison to the convergence time you'll get from geostationary satellites, which I think is around 30 minutes. So it's a boost over geostationary platforms, but not quite as good as LEO platforms. But in Europe, because of the extra processing that's done at a European level, which we don't yet have available worldwide, we can take that convergence time down to around, I think it's about 100 seconds, which is an improvement on the global capabilities. We will roll out that improved convergence time on a global basis once we have additional ground infrastructure in place in other parts of the world. But nonetheless, you will be able to achieve around 20 centimeter level of precision. Next slide, please. These are the target applications that we have in mind, covering professional, safety of life users, and mass markets. I don't intend to go through them all here, but suffice to say that there is a wide range of potential applications for the high accuracy service. Next slide, please. So I mentioned that the Galileo high accuracy service uses the E6 frequency. This is a frequency band 1260 to 1300 megahertz. This is a frequency that's shared with a number of other systems. It's shared with radar and it's shared with amateur radio. So radar is not really a problem for GNSS receivers, as they can operate between the pulses provided by radar. However, amateur radio, which is a secondary user, so this means if they cause interference, they need to switch off. We cannot operate in the presence or the close presence of an amateur radio operator. So if an amateur radio is operating within 10 to 20 or maybe even 100 kilometers, depending on the power of the amateur radio transmission and the frequency, it can cause interference to the E6 frequency, which makes it impossible to receive the Galileo HASS signal. So we're taking actions at the international level to try to improve the compatibility between amateur radio and Galileo E6. It's mainly through identifying frequencies that are more compatible. So those that don't sit on the carrier frequencies of the Galileo E6 frequency. So those discussions are going well. There will be a decision later this year at the World Radio Communication Conferences, but just asking here for support from Taiwan, if it's possible to support this idea of trying to isolate the amateur radio frequencies so that they are operating in areas in the frequency range that are more compatible with GNSS and less likely to cause interference. So that's a plea for support if it's at all possible. Thank you. Next slide, please. So this is our the next flagship. So this is EGNOS. This is the European Geostationary Navigation Overlay Service. So as I said, this augments GPS at the moment. In future, it will also augment Galileo once these standards are fully incorporated into the aviation standards that are mandated by ICAO, the International Civil Aviation Organization. So EGNOS itself has been operational since 2009. The safety of life service, which is providing the integrity feature that's required to enable this safety of life capability, has been operational since 2012. And also that EGNOS data is available over the internet since 2012. Now, just a brief word on integrity. So GNSS is inherently very reliable. GPS, Galileo are now operating for many years. They provide reliable GNSS fixes and timing on a global basis, but they don't have the required level of integrity that meets the, let's say, the safety certification requirements of organizations like the International Civil Aviation Authority. So if you are landing an aircraft using GPS without systems like EGNOS and the US equivalent WAS, you cannot use GPS for the landing. You have to have some other system. With EGNOS and the US equivalent WAS, it provides you with a 6-second warning if there are any problems in the GPS signal. So that enables you to fall back to fallback options, other options that can be used to land the aircraft. Without that integrity feature, you cannot use GPS for landing an aircraft. You cannot use GPS for docking a ship in a harbor. But with this additional integrity feature, it gives you this capability that enables it to be used for safety critical applications. Because of this, EGNOS is now used at about 600 airports in Europe. Many approaches to landing strips at airports in Europe now have EGNOS-enabled approaches, and so EGNOS can be used along with GPS to provide safety critical approaches to airports. And there are many more approaches planned in the future, as well as improvements and evolutions to the EGNOS system itself. Next slide, please. So that last slide, I forgot to say, it shows you the coverage of EGNOS, which is essentially the European area. But there are several other what are called SBAS systems, so space-based augmentation systems operating in other parts of the world. So you have the US equivalent WAS, you have a system in China called BDS or BD SBAS. You have a system in Japan called MSAS. You have a system now in Australia called SouthPan. You have the Russian system. There's a system, I think I mentioned it in Japan. There are gaps. So there's currently nothing in South America, currently nothing in the Gulf region. And there is, although it says there a SBAS in Africa, the African SBAS is currently not operational, but we are working closely with the African authorities to bring SBAS to the African region. All of these SBAS systems are interoperable. So if you have an aircraft flying from Europe to the US, the same type of signal can be received to enable it to be used for safety critical applications. Next slide, please. So now I'm talking about the third flagship. This is Copernicus. This is our Earth observation system. Next slide, please. So in, let's say, this must have been early 2000s, the Copernicus concept was developed, and in 2014 it was finally approved as a European Union program, the Copernicus system. Its primary intention is to monitor the Earth, its environment, and its ecosystems to ensure that citizens are prepared and protected for crises, security risks, and natural or man-made disasters. So it provides information on a free and open basis. You can download Copernicus data from a number of data hubs throughout the world, and you can use that data for whatever purposes that you need to. It's a tool that can be used by authorities to help them with their economic development and also for building economies. So it really is a very powerful set of data provided by the Copernicus Earth observation system, and it's operational 24/7, providing data based upon a number of satellites currently in orbit around the world. Next slide, please. So I mentioned the satellites. So there are a number of different families of Copernicus Sentinel satellites. So you can see there all the Sentinel satellites on the left-hand side. So these are the Sentinel satellites that provide the data that is essentially the cornerstone of the Copernicus system. But in addition, on the right-hand side, you can see that we have a number of contributing missions. So these are missions that are essentially operated by third countries. So these are countries outside of the EU, and these provide additional data that can contribute to the Copernicus system. These maybe enhance the capabilities of Copernicus, maybe improve the resolution, maybe improve the range of sensors that are covered. And this can not only benefit Copernicus, but it also benefits the contributing missions, because the two can work in conjunction to essentially enhance the data and services provided by each of the systems. But also we have what we call in situ systems. So these are ground-based sensors or ground or air-based. So maybe weather balloons, for example, that can also contribute data that essentially is acting as a reference for the data provided by Copernicus. So in conjunction with all of these different sensors, it enables us to provide a very accurate picture of the Earth's atmosphere, the Earth's surface, and the oceans that we all are surrounded by. And together, this data is combined into 6 themed products, and these are provided to users through a number of websites that we have dedicated for each of the 6 services. Next slide, please. So as I mentioned, the in situ data is provided from ground, sea, or airborne sensors. Essentially, it's used to provide reference and ancillary data to the Copernicus system. The primary emphasis of these is that they can validate and calibrate the Copernicus products. Essentially, having a reference for the Earth observation data gives you a much more reliable service to users. Next slide, please. So I mentioned we have 6 themes for the Copernicus data. These are monitoring the state of the Earth's environment. So there we have the 6 cross-cutting thematic services. We have the atmospheric monitoring, the climate monitoring, the ocean monitoring, the emergency management, and then security monitoring, which is just for EU member states. Next slide, please. So this is the land monitoring service. So this is geared to provide data that is most useful for applications that are looking at the use of the land. Next slide, please. And then we have the maritime service. So this is providing data that's used for maritime applications. Next slide, please. And then we have the atmospheric monitoring service that can monitor things like air pollution. Next slide, please. Then we have climate change. So this is monitoring parameters that are important for monitoring the effects of climate change on the Earth. Next slide, please. And then we have the disaster or its emergency the emergency system, emergency service. So this enables, in a disaster, additional data to be provided by the Copernicus system for helping authorities control and manage disaster situations. Next slide, please. And you can see here from this chart how Taiwan has made use of this service in the past to manage and to mitigate the challenges provided by disasters such as typhoons in the region. Next slide, please. So in summary, the Copernicus system is a system that provides data free of charge. It's aimed at protecting people and assets around the world. It provides state of the Earth's environment. It's aimed at providing and improving the environmental policy effectiveness for authorities. And it's a key tool for helping us to monitor climate change and the effects of climate change on our environment. And for disaster situations, it can also provide information that can help authorities manage the situation. Next slide, please. Now, the final slide of the final system in our EU space program is IRIS². So the infrastructure for resilience and interconnectivity and security by satellite. Next slide. So this is a program that was approved earlier this year, and you can see there the President of the European Parliament signing. In fact, I was at an event yesterday, a running event, and she was there with us, so I got to meet her. And then other key officials from the European Parliament there in the background. So documentation there on the right-hand side. It's the regulation that essentially gives the green light to the go-ahead for IRIS². Next slide, please. So IRIS² has two key aims. It's to provide secure, autonomous, high-quality, reliable, and cost-effective satellite governmental communication services to government authorized users. So that's the governmental side of the program. But then it has a second side to enable commercial services or services offered to governmental authorized users based on commercial infrastructure at market conditions. So this is a side that essentially is like something like Starlink. Maybe it won't be the same number of satellites as Starlink, but essentially it's designed or will be designed to offer services very similar to that of Starlink, but from a European system. Next slide, please. So IRIS² is going to be designed to maximize the use of disruptive technologies. So these are technologies that are the forefront of innovation. It's also designed or will be designed to maximize the use of open source technologies, open standards, and interoperability. To maximize the use of essentially standard-based equipment where it can be used, and that will minimize the costs. And we want to make sure that we have a good involvement of the smaller companies, so the SMEs and the startups, which are often the source of the most innovative ideas. So we hope those to be parts of the IRIS² system. Next slide, please. So IRIS² itself will be a global multi-orbital secure architecture system built upon the existing EU programs GovSatcom, which provides governmental communications from geostationary satellites, and also EuroQCI. So security is a key part, and EuroQCI is a European project to have quantum communications at ground level between the member states. So IRIS² will bring that quantum capability to satellites, and this will enable us to provide secure communications to users around the globe. So these governmental users within the EU. So it will be providing these services from low Earth orbit satellites and geostationary satellites, potentially with also a MEO component, a medium Earth orbit component. So it will offer strong encryption, quantum encryption. It's designed to be innovative, and it's designed to be scalable. Next slide, please. So here are a range of the services that we anticipate for the IRIS² system. So as you can see, you have governmental services on the left-hand side and commercial services on the right-hand side. We are still at a very early stage in terms of bringing IRIS² to life, to implementing it as a system, but we have high hopes for the applications that can be used, not just in government, but also in applications for civil users. I think I've now run out of time, so that is my last slide. So I thank you for listening, and if you have any questions and if there's time, I'm available here to answer them. Thank you.
Thank you so much, Dr. Dominic Hayes. We're sorry we're running out of time here, so thank you once again for joining us online. Thank you, Dominic. Thank you.
It's my pleasure.
All right. Astrolites Yes, we can see you, Dr. Vigmontes Tonkas. The floor is yours. Ladies and gentlemen, please welcome Dr. Tonkas.
Good afternoon. Thank you very much for the possibility to present the Astrolight and also our vision to the space-based optical and quantum communication. So actually I'm representing the company, but I will try also to give a bit broader overview about the situation in the optical space communication. Next slide. So the presentation outlook will comprise a short overview about the company. Then I will give some overview about the space data growth and requirements on optical communication. And I will present the products and services that are developed in the company and also some actual fiber-based sources and photonics components for classical quantum communication, and we'll end with the conclusion of the presentation. Next slide. So as I already said, Astrolight Vision has become a go-to company for satellite-to-earth optical connectivity, and we would like to solve all the relevant problems in a practical way that could be important for the companies, but probably also for the agencies that require a high data rate communication from the space to the earth. Next slide. Short company overview. Astrolight is a spin-off from National Lithuania Research Institute called FTMSC and Vilnius Tech University Aviation Institute. It was founded 2019. Currently, we have 20 employees, but the founders have more than 10 years experience in space, in the telecom and laser industries. And as I already mentioned, Astrolight is the supplier of free space optical communication systems and solutions. Next slide. Very short overview what we have done in the last 4 years. So we started with the development of fiber-based components, and first product was 1.5 micron fiber amplifier. And we started to test optical links. The first demonstration was the free space optical links on the ground between the Vilnius TV tower, and other side was arranged at a high store building. So we established and demonstrated 1 gigabit per second free space optical link. In late 2021, we get some pre-seed funding and also started cooperation with European Space Agency. And now we have already several contracts, and we have got also commercial interest in our products. And in 2022, we had successful demonstration of a satellite link between the space and our ground station. And it was demonstrated between the Stuttgart University flying laptop satellite and our ground station, once in Lithuania and once in Tenerife. I will present a bit more detail later on this experiment. Next slide. So the business itself, or the data communication in space and from space to Earth, it consists of several segments that of course comprise the satellite itself. Mostly it could be remote sensing satellite that collects a lot of data, but it could be also telecommunication satellite, and now many low Earth orbit satellite, they already implement inter-satellite links and optical inter-satellite links. These satellites could also collect information from the ground, for example, Internet of Things. And then, of course, all this information should be sent to the ground infrastructure, to some cloud services. And many of these data are used for big data applications and are provided for the end users. So we position ourselves as a hardware and probably in the future also service provider for downlinking the data from the satellite to the ground station and providing it to the ground services, to the cloud service. Next slide. So a bit about the requirement. The space data demand grows every year, and according to the Northern Sky research, in the 2030, so the amount of data that should be transferred or downloaded from the space will increase by more than 10 times. And one of the examples is, for example, the comparison of the European Sentinel-1 and the planet Sentinel-Rose-L. So you see that for the Sentinel-1, the data that are required for the download per day is 7.2 terabit. And for the radar satellite that is planned to launch in the future, so it will be almost 10 times more, like 97 terabits per day. And that means that classical radio channel could be not enough to do such a service. Next slide. So shortly about how it looks like. So now all the radio links and radio spectrum are located in so-called C, Ku, Ka bands in the microwave spectrum of the radio, and there are some new ranges that are planned to be started to operate, so-called Q and V. But anyway, all this spectrum is in the range maybe about 60 gigahertz. And if you look at the optical domain, so we have about at the order of 10 to 6 more spectrum. And it's not only the visual spectrum that we can see by our eye, but it's also part of infrared spectrum. And totally it's more than 500 terahertz. Of course, that's also not all the spectrum is practically available for implementation, because it depends also on the existing technologies, on the existing materials, where we can get efficient optical signal generation. And for example, in the telecom C-band at 1.5 micron, we have approximately 5 terahertz. And if you use it for the dual transmission, I mean duplex transmission, so we need also have some gap in between the send and received signal. So generally we have about 2 terabits available, but anyway, it's much more than in the radio spectrum. And another one also distinctive feature that optical communication, it's much more resilient to the jamming, hacking, and the data rates, as I mentioned, are 10 times higher than in a radio spectrum. Next slide. Shortly about the situation on the standards. So it's a bit related also to the business, and now mainly branches or standards that are developed and discussed. It's for the moment not accepted, maybe common standard for all the optical communication, but first one is so-called high photon efficiency standard, and mostly is used for the planetary communication, deep space communication. Another one standard is so-called a high data rate communication. It's mostly implemented by BPSK or QPSK coherent communication, and it's used of encoding on a high data rate communication. And the third one, it's so-called low complexity, and it's used mostly for small satellites and inter-satellite links. And we are looking specifically at this one domain. And this standard was also developed recently by Space Development Agency in the United States. And it's more generalized for different terminals, both for inter-satellite links, but also for space to ground, space to vehicle, space to high altitude platforms. And we consider this as one of most practical standards that we would like to approach. Next one slide. As I mentioned, that these first two standards, this high photon efficiency, and high data rate, they are mostly used by bigger space agencies like NASA, like ESA. And of course, that's a very great endeavor. And for example, they are dedicated for the demonstration for terabit scale communication for the data relay between the Moon and Earth, for the serving the coming Orion human flight, and to provide the mission with a high definition television. For example, also one of such examples are Psyche mission for the serving the mission and exploring the asteroid belt between the Mars and Jupiter. But mostly the terminals are quite big, both on the spacecraft and on the ground. Also, the telescopes are big, in the range of 1.5 and coming up to maybe 3 or 4 meters. And for practical business, it's a bit maybe too high investment, but of course it's very interesting, and it's very suitable for such research applications and space applications. Next slide. Another one very interesting also challenge was raised by DARPA, and the goal was to provide so-called 100 triple product or 100 triple solution. That means to develop a terminal that would be space adaptive, and this node could communicate with different systems, and it could provide the 100 gigabits, use 100 watts, and cost not more than $100,000. It is of course quite a big challenge, but in the future I believe it will be one as a more interesting application of one most interesting solution. Next slide. Very shortly about the ESA programs. ESA has two big programs dedicated to its optical communication. One is called Hydron. It's for a terabit optical transport network in space and space to ground. And the goal is to provide with terabit class data links. Probably it will be something like 10 times 100 gigabits, and for seamless integration into terrestrial networks. Next slide. Another one big program is Saga. It's for security and cryptographic applications, and that's mostly about a quantum key distribution, and there are several stages, and one is for the LEO, or low Earth orbit satellites, and another one is for geostationary satellites. Next one. So the optical communication itself, it has different requirements compared to the radio communication. And first one is the clear sky. It should have also low humidity, low dust concentration, and such a site has to provide good access to infrastructure. And even at such a sites, remote sites that have very good clear sky, it normally not provide 100% availability as it is in the radio communication for the good availability of 99%. So according to our estimations, at least 3 sites should be available. Next slide. And now I'm coming back to the Astrolight products. And first product that we have demonstrated for this satellite to ground mission was a transportable station called Optical Ground Station 1. It's relatively small, 11 inches. It's about 30 centimeters, but it's capable to download the data rates about 1 gigabit. And we demonstrated tracking accuracy about better than 10 arc seconds. And next one slide. And distinctive feature of this optical ground station that it could be packed in 3 boxes, checked as a flight standard passenger baggage, and could be transported to the remote site. And such experiment was provided not only in Lithuania, but also together with ESA at Tenerife. And during this mission, next one slide, we have been capable to track the satellite and to receive the signal with a relatively small telescope, like 11 inches, and coupled the light into the detector. And they have been tracking for approximately 4 to 5 minutes with the accuracy of 3 arc seconds. But one of the problems that we have noticed that the tracking was not very stable from the satellite side, and that's because the satellite doesn't have the beacon and is not suitable for the line alignment between the ground station and the satellite. And actually, the satellite pointing was only based on the coordinates of the mission, and that means that for the telecom grade signal availability, the tracking both from the satellite and both from the ground station using the beacon would be required. Next one slide. The next optical ground station called OGS-2, it's already bigger, and it has 14 inches telescope that's about 40 centimeters, and we consider it's suitable for the download data rates up to 12 gigabits. And we are now testing this optical ground station, and it will be already used as a permanent installation. And our plan is also to cooperate with other missions and to provide this service to the other missions and optical communication provider as a data service. Next one slide. The next one product that we are now developing, and it's in the stage of approximately TRL 5. So that means that we have the engineering model, and we are doing now the different space grade tests like vibration, like thermovacuum, and radiation tests. And the plan is to launch next year and to have the demonstration, and that's the space terminal of the size of approximately 1.5 CubeSat unit. It has 1 watt optical power. The wavelength is this use the standard telecom 1.5 micron. It will have also possibility to receive the beacon. It's planned for the 800 nanometers, but probably if there will be requirement, could be upgradable to the C-band to 1.5. The modulation and on-off keying, and it's quite simple, but it will be also cost effective, and we would like to demonstrate it as a bundle, as a service between the satellite and our ground station, and demonstrate that this service could provide at least several times higher data rate compared to the radio communication, and it could be installed on relatively small satellites, for example, remote sensing satellite, and provide video effective data download from the space to the ground. Next one slide. Now a bit about our research and development. We have several contracts, as I mentioned, with the European Space Agency, and one of such product that we are developing is so-called scalable ultra-short pulse actively mode locate source, laser source, and the distinctive feature that we modulate not the laser diode to get the data transmission, or we do not use an external modulation, but we modulate the laser cavity itself. And what is the reason and what is the distinctive feature of such a source? That we have in such a way the possibility to scale the pulse peak power and energy by changing the pulse repetition rate. And this feature could be very interesting for the adaptive rate communication, and for example, also if the the link conditions or the distance of the satellite is changing. So there's the possibility to save the power and to provide with the higher peak power. And that means that increase or the data rate or the distance. And we demonstrated the operation of such a source. We get a stable generation of the signal. Next one slide. And we demonstrated also practically that pulse peak powers and energy scales by changing the pulse repetition rate. And the next one slide. And now we are doing different data modulation experiments to be able to transmit some relevant data using the source. And basically, now we are using 25 megahertz fundamental repetition rate and quite a short 60 picosecond pulse duration. And it could be also shorter, and for some applications, it could be important to have very short pulses. The pulses can be modulated up to 12 gigabits, and the source has also very high extension ratio between the pulse time slots, and that's because it's a characteristic of mode-locked lasers. And it could be important, for example, for quantum communications, when you should have very high so-called contrast and also good with the pulses. With the pulses, you could reach much more efficient locking of the detector and getting better results on receiving the photon signals. Next one slide. Now a bit about our work on the quantum communications. So very shortly about the sources that are used in overall. So one type of the sources are so-called V-coherent photon sources that actually the states modulated similarly like in a classical telecom, but just they are very weak to reach single photon level. And the probability of such a modulation that a single photon, you get probability is about 90%. Probability of zero for optical vacuum is about 9%, and getting multi-photon states is 1%. And that's maybe most popular standard that it's used now in the quantum communication experiments. Another one is so-called heralded single photon source, when you generate pairs of single photons in highly correlated states or entangled states. And mostly the type of this sources using spontaneous parametric Dom conversion. And we have been using a bit different approach for wave mixing. I will show shortly how it looks like. And the last one are, of course, deterministic single photon sources like quantum dots, color centers. But for the moment, I haven't seen the demonstration in a practical application. But of course, in the future, will be maybe one of the main quantum sources used in the quantum communication. Next one slide. In means of entangled photon sources, there have been several demonstrations also in the space. One of that is very famous mission of Mitzius of Chinese satellite, and it was demonstrated using a spontaneous Dom conversion. But maybe distinctive feature from the source that we are developing, that this source was arranged at relatively big satellite, like a microsatellite with a weight 630 kilos, and it was the bulky construction. Another one application was demonstrated already on the smaller satellite. It was the Singapore project, like SPQS satellite. But principle, it was also the same. And the next one slide. And what we have been developing, that is fiber-based source. That means that reliability of such a source, it's bigger, and it's also much more compact. And another one interesting feature that we can drive it using it in pulsate regime, and and it will have also better synchronization and better possibility to synchronize the detector on the specific time slots. And we have been using two stages of such a source, one of the creating of the specific wavelength to generate the entanglement photons, and another one stage was used for the generating of these entanglement photons. And we have got about 1 megapairs, that means 1 million single photons per second at the fidelity of 97% and about 500,000 photons per second with a fidelity 99%, and the power consumption was the pulse generator about 2 watts and the complete system about 9 watts. And we think that it won, let's say, possibilities to use it also on the smaller satellite missions. Next one slide. And comparing to the missions that have been flown out in the space, so the power generation rate is at a similar level, even with such a big satellite like Mitzius. But distinctive feature that we had very short coincidence window, like 10 picoseconds, compared to the nanoseconds in the spontaneous down conversion scheme, and it could be useful for the more effective detection of the single photons. Next one slide. And maybe last one thing I would like to mention in the means of technical presentation. We're also looking for other schemes. That's cooperation with Bern University and Geneva University, that there are possible solutions that have a mix of classical communication and quantum communication. And according to this approach, if you have some restrictions or so-called exclusion area, that means that you can receive the signal at the dedicated place and could guarantee that this place is secured. And in a satellite case, it could require a small area. For example, for LEO, it's about 13 meters. And that means that the signal drops. And if you are outside of this area, and it was theoretically proven that, for example, with the degradation of the channel outside of this exclusion area, and having signal just at 10% of such a signal outside of this area, you can provide about 60 or 70% of secure private communication relatively to the generated signal. That means if you have, for example, 1 gigabit of signal that you are, or data rate that you are transmitting, that means you could have in such a way about 700 megabits of the private channel data rate. And that is, of course, much more compared, for example, to the standard quantum key communications, like 10 kilobits that it was demonstrated at Mitzius mission. And another one distinctive feature that is much more less sensitive to noise and signal dynamics and could be used possibly also in the daytime. So we think that also this mixed approach would be very useful in the practical communications. And next one slide. So concluding, we would like to show and present that space data growth is huge and will reach, the requirement will reach more than 10 times by 2030. And so that means that new frequency spectrum for the data transmission is required, and that's, of course, could be optical communication and different wavelengths, maybe not only telecom, but also other infrared or even visible range. So Astrolight develops cost-effective hardware solutions of optical ground stations. The telescopes are in the range of 11-14 inches. And next year, we plan to launch 1.5U space terminal that will have capability of 1.25 gigabits on-off key modulation, and that could be useful for different small sat missions and installed, for example, on the board of remote sensing satellites. And we plan this demonstration next year. And we also develop different fiber-based sources and amplifiers for classic or quantum implementation. And if there are some specific problems that could arise in solving different tasks of the mission, so we would be happy to serve. And we are looking also for cooperation in the field of optical ground services with other optical satellite missions. And we would like to develop it to the network and provide it as a service. So next one slide, and that concludes my presentation. So thank you very much for the attention.
Thank you very much to Dr. Ignatius Panthas. Thank you again, and thank you for your time. Thank you. All right. Ladies and gentlemen, we take a Julius as bonus. And our speaker is going to share with us the nano avionics experiences with Space Project. So now please join me in welcoming Dr. Julius S. Models, Business Development Manager of Nano Avionics. Let's welcome our speaker, Julius.
I hope you can hear me well.
Yes, we can hear you.
Very good. Thank you. Thank you for having me in this event. I'm really grateful for this opportunity, and I would like to use it to present Nanoavionics as a space company from Lithuania and tell about what we do and what are our main services and activities. And we are the space company from Lithuania, so I'm really happy to tell you more about it. So please, next slide then. So we are, as a company, as Nanoavionics, we aim to provide our customers with a more cost-effective satellite buses. And this is our specialty. We call ourselves bus experts. So the idea is to design and manufacture the satellite buses that are cost-effective, and also they can accommodate different payloads from the customers, or we can provide even the full mission services for our customers. And in this presentation, I will tell you all about the services that we provide, the equipment that we manufacture, and other things that we do as a company. Next slide, please. So yes, let's start from the key things, three key main things. Well, very simply saying that, make the mission successful is, of course, our key activities is concerning the space segment and the hardware of the satellite buses that we manufacture and integrate satellites in Lithuania and in Vilnius. And the other activities that we provide for our customers is, of course, the launch integration and the launch itself. Just to be clear, we do not build the rockets by ourselves, but we partner with SpaceX, with other launches to launch the satellites in orbit. And of course, last but not least, is the operations of the satellite. We have our operation center in Vilnius, and we use the ground stations all over the world to
Seems like we are having some connection issues. Julius, are you still with us online? We just lost you, Julius. 不好意思哦，目前可能讲者端的连线好像有点问题哦，所以暂时听不到讲者的声音。我们可能给讲者一点点时间，让他再连一下。Let us give Julius 2 minutes. Let's see if he gets back online and continues with the talk. And if it doesn't work, maybe we'll give him a few minutes. We'll see how it goes. If it doesn't work, maybe we'll go to the next talk first because our next speaker is here with us in the room. 我们先看这样 OK 吗？不好意思，我们先等个几分钟，看 Julius 能不能再上线啦。如果不行的话，我们下个讲者就在。 how it works this time. Yes, welcome back. So happy to
Yes.
see you again, Julius. Yes.
Yes, I'm happy to be back. Actually, had some network issues, but seems to manage to solve it. So we finished. Where did you lost me? Could you please tell me?
Right at the beginning of the slide. Yeah, you
Okay.
can. Yeah.
So yeah, well, let me go through it again. And so the main three things that we do for our customers is the space segment, the hardware design, the development and manufacturing and assembly, and launch integration, and of course the operations. Just to be clear, we don't build the rockets ourselves. Of course, we use SpaceX rockets. We use other providers in the market available to launch our spacecrafts, but we support the integration and all the procedures associated to the launch. And last but not least, of course, the operations. We operate the satellites for our customers using the ground station network, which is all available ground stations on the world. Next slide, please. Yeah, so few major facts about our company, about NanoAvionics. So the company was established in 2014. Now the company has more than 280 employees globally. We have people working from various countries. And space engineers is not something that you can find very easily. So we gather the people from all over the world. As of now, our team gathered more than 120 missions experience. That by saying that, I mean that we either provided the products for the missions, either supported them on engineering services or provided the spacecraft by themselves. So, and of course, the best figure that describes the experience of the company is that 27 launched satellites and still counting. Practically every transporter mission with SpaceX is with our satellites. As of now, we have 4 offices, 2 of them in Lithuania, in Vilnius and Kaunas, main integration facilities in Vilnius, office in UK, mostly engineering support, and also the office and integration facilities in US. Next slide, please. So now a bit more details about our services and products. So I'll start with of course with the space segment and the satellite buses. So our product range starts from 6U satellites. So as we simply call them shoeboxes, I'd say, or we call them the smallest satellites that can really bring benefits to customers. And the largest one that we are currently designing is MP42D, which is capable of accepting or accommodating the payload up to 75 kilograms. So these satellites are mostly, they split into 2 main groups. So as we call them CubeSats and small sats. The CubeSats are based on same subsystems, even ECS components are mostly the same on these satellites. So they have plenty of heritage, they are reliable. And microsats, the small sats, they contain some of the same components that were used and have flight heritage from the missions with the CubeSats. But there's also different actuators needed and control systems needed for the bigger satellites. Also, power systems are upgraded. But even when we are designing new components for the spacecrafts, they are based on the experience gathered with the previous missions or the hardware developed. So next slide, please. This is one of the example of what our satellites can do. This is the satellite MP42, the first small sat launched by NanoAvionics in 2022, April 1st. So it has 2 cameras on it, which is our internal project. And these pictures taken that you can see is our internal project, not for the customer, but purely for the experiment. And the experiment was, I mean, the engineers wanted to see the spacecraft in orbit and to see how it looks and what is going on with it to gather more data. And it actually turned out to be very impressive and very, let's see, it brings a lot of good emotions to our engineering team to see these pictures, to see what the satellite can do, even with a very simple camera. And it was, of course, modified by our engineers, but it brings very nice pictures from orbit to us. This satellite in particular, the MP42, contains in total 6 payloads, and 4 of them are from the customers and 2 are internal payloads of ours. So one of the camera is one of them. Thank you. And next slide. Launch integration. Yeah, so I think this is, I mean, all these parts are very important for the successful mission. So we try to provide the services or the support to the customer as much as possible at all these stages, including the launch. So the launch integration is, and the launch itself is you know, it's a critical thing. We rely on partners for the hardware, launch hardware. By that, I mean, satellites have to be deployed from certain boxes or rings, which we do not develop internally. We have trusted partners for that. We have plenty of heritage with those partners. They also provide support in the launch site and integration. And we participate in all these stages to test the satellite, to prepare it for the launch, and to perform everything that's needed. So currently, the most launches we're doing with SpaceX, but we also have experience with PSLE. We launched with them, with Vega, Rocket Lab as well. And yeah, that would sum up launch integration part. Please, next slide. Operations. So operations is another crucial thing for the mission, successful mission. Currently, we have 27 people in the operations team. Our operators are working 24/7 in shifts to provide the full support for the customers when it's needed. We are operating using our ground stations that we have, even our ground station in Vilnius. We also use KSAT network, Leaf Space network, to bring bring to the customers as much coverage as possible. Next slide, please. And this is like a general overview of the operations and how, in general, I mean, satellite mission happens. So it starts all with well, for us, it starts way before by designing the spacecraft, but in what is shown in this picture after the launch, satellite is of course controlled by using ground stations to send the commands, then send data back to the ground, and our customers can have it deployed, let's see, shortly, but very quickly in their service, and they can analyze it, work with it, and yes, I think that would be mostly simple overview of how the operations happen. Next slide, please. Yes, and of course, the experience and the customers that we work with. So it's I mean, we are now working with 47 countries, and we have supplied the components or the satellites or the other services for 47 countries in total. And we have customers in the governmental, from the governmental area or defense area. We have commercial customers from new space, even from old space. You can see quite familiar names in the list. And also we are working with research institutes and universities as well. So it's quite a broad range of customers, and we have very, I'd say, successful missions with them. Next slide, please. And this is the list, or say, a showcase of our the missions that we can share, at least that can be disclosed and presented. So in this list, you will see the missions. Like the first on the top is the free EU missions, and we go all the way with the big satellite MP42, and we are still, this list will be expanding quite a bit, and in general, I'd say looking into applications of the satellite missions that are, I think I get this question quite often, and I think it's interesting for you as well. What is the how in percentage wise, how many missions we do for the Earth observation or the communications or any other application? So it used to be that the communications were the most of the missions that we did, but over the last 2 years, Earth observation missions took over, and as of now, I'd say about 60 to 70% of the missions are Earth observation missions in some way. It can be, it can be thermal imaging, it can be high resolution imaging, like simple imaging. It can be monitoring, signal monitoring missions, etc. There's quite a bit of them. And yes, I'll be happy to answer your questions if there are any. That's pretty much sums up my presentation.
Thank you very much. Julius, we still have some time. Want to see if we have any questions for you here.
Sure.
Do you have any questions from the audience here? Yes, we got one question. Please also let us know who you are, and thank you.
I'm Begonia. I'm from Ubicon, the CEO of Ubicon. Just a curious question. You mentioned, I didn't know whether I hear wrong information. You mentioned that the majority of the satellite application currently mainly for the observation, right? Is that true?
Yes, that's correct.
Okay, so my question is, do you see that it's changing now? Do you see the application for satellite is changing other than observation? Is there any other application you are now seeing?
I think this trend is dictated by the available payloads in the market. In previous 5 years, there were quite a few companies that developed the payloads, imagers, or developing good quality payloads that can be used. And the customers just they found this opportunity for reasonable cost to start doing Earth observation missions. And I think that was the main reason that there was quite a lot of Earth observation missions. And this trend continues, I'd say, for upcoming 1 or 2 years at least. And we will have more and more Earth observation missions. But communication missions are also as much important as Earth observation, especially something similar like Starlink, or I think that in a couple of years we'll have more communication missions coming in as well, because a lot of companies are working on the very impressive payloads, I'd say, and it should lead to the growth of this communication market as well.
All right. Any more? Maybe one last question before we close this session. Okay, so if you have no further questions, please put your hands again for Dr. Julius Smolenus for his very, very insightful observations. Thank you again.
Thank you.
Right now? Yes. Okay. So we can see you, Dr. Marek. So the floor is yours. And ladies and gentlemen, please join me in welcome Dr. Project Marek.
Thank you very much for the warm welcome. First of all, I'd like to introduce myself. As mentioned before, my name is Marek Krawczyk, and I'm representing Exatel, a company from Poland. So first of all, I would like to mention the title of my presentation, Orbital Solutions for Post-Quantum Cryptography. So at the beginning, I would like to explain that by post-quantum cryptography, I here mean the general idea of cryptography, problems of cryptography that it will face after the development of quantum computing. So it may be confusing because post-quantum cryptography usually refers to software solutions, certain type of cryptography algorithms. But in this presentation, I will go beyond this and will go into a physical layer of cryptography. I will refer to this in the later part of the presentation, but now I just wanted to clear this out, that what I meant about in the context of post-quantum cryptography here. Okay, so could I have a next slide, please? So first of all, I would like to say a few words about the company that I represent and explain why the company is interested in the problem of cryptography in general. So my company is a telecommunications operator that is working mostly in Poland, but also is operational abroad. And the company has various areas of activity. The main activities is obviously telecommunications, but also because of the clientele that we serve, we provide services and products in cybersecurity, SATCOM, and integrated services. And we provide these products and services to operators, other operators, businesses, public sector, and critical infrastructure providers in Poland. Next slide, please. So on this slide, you can see the extent of the network that we own and operate in Poland. It covers over 3,600 telecommunication hubs and over 21,000 kilometers of fiber optics network spread across the Poland, but also crossing the borders of the country. So as you can see, the responsibility of our company when it comes to securing that kind of extensive network is really high. Could I have a next slide, please? And as mentioned before, the company is not only working on the territory of Poland, but also has points of presence abroad. And this way, we are connecting our network to other networks, global networks around the globe, and we serve as a transit point for communications coming, for example, from Western Europe to Asia. So if somebody calls, for example, from Brussels to Taiwan by phone, most probably the voice traffic will go through our network. Could I have a next slide, please? As a company, we are also interested in being part of the space industry ecosystem. And for that reason, our daughter company initiated the creation of a space technology cluster, that is a cluster of companies as well as universities and research institutes that is aiming for the development of space technologies to serve national and commercial targets. So as a company, as an operator, we are interested in fostering the relationships between public institutions and companies. Excuse me. I have reverb headphones. I'll try to speak anyway. So the connection between the business and the institutions and the recipients of space technology is very important for us. Could I have a next slide, please? Okay. So now I would like to go to the main topic of my speech today, the optical key distribution, which we think would be the revolution in quantum cryptography that will happen in the coming years. Could I have a next slide, please? So first of all, we would like you to understand why we, as a telecommunications company, we are interested in the technology and we see the need to engage in space technology development. Well, first of all, we are aware of the fact that the companies and scientists around the world work very intensely on the development of quantum computing, which will make the currently used encryption methods obsolete. This is let's say a paradigm that what we're working in. In the couple of years, we will face, most probably we will face a situation when currently used encryption methods will be invalid, and we have to prepare ahead of the time in order to prevent the data sent through our network to be eavesdropped because of the demanding market that we operate in, so B2B and B2G market. We are constantly looking for methods to increase the security of our network. The clientele that we have is very demanding. We handle sensitive information, so we need to be prepared not only to serve current needs, but also the future security needs of our clients. And what is also very important, we are responsible for communications in the realm of critical infrastructure. So we need independent solutions that are flexible enough to be applied both to public and military clients. And we are now facing a situation where operators like us have a very limited choice of very few quantum key distribution hardware vendors. And that means that we are kind of dependent on their offer, and we have very little space for price negotiation or feature negotiation. We basically, if we would like to be prepared for quantum key distribution deployment right now, we would have to just take what's there in the market, and that's not a very comfortable situation for an operator, not only for us but also others. Can I have a next slide, please? Okay, so now to explain a little bit of background of why we are investing and interested in this area is a couple of notions that I would like to underline. Most probably, many of you already are fully aware of this, but I just wanted to set a background to what will be said later on. So first of all, we know that what is the basis of classical cryptography systems being used right now is computational complexity. So, for example, factorization, which is an operation to identify numbers, which product is equal to a known number x, is the basis of the most of classical cryptographic systems. And we know that factorization algorithms run in exponential time, with respect to the length of the number being decomposed. So the base of currently used classical cryptography systems like RSA that are commonly used to secure transmitted information are based on this computational complexity. However, we know that as mentioned before, many players, national and commercial, they are developing quantum computers, which are and the quantum computer is a computer that exploits quantum mechanical phenomena. And a scalable quantum computer could perform some calculations, including factorization, exponentially faster than any modern classical computers. So the problem is that the basic principle that was serving us in securing communications using classical cryptography systems is no longer valid. If we have a hardware that allows us to calculate problems such as factorization in a much faster time in a matter of seconds or milliseconds, then this security measure is no longer valid. So we need a countermeasure for this situation. And with help comes quantum encryption. So quantum encryption is a data encryption using the quantum properties of light. So this method is inherently resistant to decryption using quantum computers. And it secures against the computers and the fact that they allow for relatively fast factorization. Could I have a next slide, please? So let's say the practical implementation of quantum security is called quantum key distribution, and it's a process of exchanging a secure cryptographic key using quantum properties of photons. An example of such a key exchange method is the BB84 protocol. So where the sender and receiver need to exchange polarized single photons to establish a secure key. But such operation puts a high requirement on the amount of tolerable noise and losses introduced by the physical channel, for example, fiber optics or atmosphere, if we consider sending such a signal through atmosphere or through satellites. And and the requirements are also high on the side of performance of applied optoelectronics components. And the requirements make the method quite expensive in terms of complex hardware and not particularly effective in terms of the length of the generated secure key. But there's an alternative, which is called intensity modulation or direct detection optical key distribution. And this is a process of exchanging a secure cryptographic key using quantum properties of light. This new method has been created where a transmitter sends slightly intensely modulated light with a power level used in conventional optical communication systems. And the receiver directly detects these changes with a conventional photodiode followed by a threshold processing. Its security, the security of this method relies on the slight intensity modulation being masked by quantum noise. And this approach is, in principle, requires relatively minor modifications of currently used optical transmitters and receivers, and can be executed using standard telecommunication components. Could I have a next slide, please? So this table makes a brief comparison between the two methods, the quantum key distribution and optical key distribution. Both of these methods provide security against realistic eavesdropping scenarios. So if somebody wants to take over the communication, listen to the communication and decode it. Both of these methods provide realistic security. By realistic, I mean in quantum key distribution, the method secures against such extreme scenarios like putting a quantum computer between the receiver and the recipient of the information. The optical key distribution system does not provide such high level of security. However, this scenario is quite abstract. If we imagine a situation when we have a sender of the quantum key on the satellite, it would be virtually impossible to put a quantum computer between the ground station and the satellite that is that's going around the orbit. So this is what we mean about realistic eavesdropping scenarios. The second point is the hardware complexity. In the case of quantum key distribution system, the complexity is really high. You have to have a dedicated transmitter and receiver to send and receive single polarized photons, which is a very sensitive operation. In case of optical key distribution, the hardware complexity is much lower, because what you need is a modified optical transmitter and receiver in order to execute such communication. Also, the difference is quite big in a scope of estimated amount of secret key generated per satellite pass. In case of quantum key distribution, we are talking about the scale of 300 kilobits, when in case of optical key distribution is in a measure of 200 megabits. So we're talking about around 1,000 times more key generated per satellite pass. And the difference is also in the area of availability of optical channel for parallel secure key generation and data transmission. In a case of quantum key distribution, you have a dedicated system just for that, for sending polarized photons between the transmitter and the receiver. However, in case of optical key distribution, you can send both the class, let's say, data stream using optical channel, optical communications. In parallel, you can send the secure key. So you have, let's say, 2-in-1 solution when you do not have to compromise on the availability of the optical channel for communication. And the overall system development and deployment utilization cost in case of quantum key distribution is much higher in comparison with optical key distribution. So we can see some obvious advantages of the second solution. Could I have a next slide, please? We, as a company and in collaboration with Polish universities involved in the project, we propose the development of a solution to enable optical quantum encryption using cryptographic key distribution based on optical communication technology. And this will be made possible by creating a system, like building and launching a satellite to test an innovative transmitter combined that would combine the ability to transmit both data and the cryptographic key in parallel. And the reason that we are interested in this scope is because the quantum cryptography considered a new standard for in-transit and stored data protection. And we, as a telecom company, this is our business, securing the in-transit and stored data for our clients. So currently we are gathering partners and funds to build such custom nanosatellite system for quantum encrypted optical communications together with the dedicated ground segment. Could I have a next slide, please? So The system, if developed and successful, could be utilized in a number of scenarios. So, for example, it could be utilized as a top-level security measure for governmental and military satellite downlink transmissions. We could provide a satellite-based cryptographic key distribution service for securing long-distance post-quantum terrestrial data transmissions. So, for example, we could deploy ground stations in Europe and in Taiwan, and secure communications between Europe and Taiwan using classical, let's say, fiber optics channels. We also would be overcoming cost and distance limitations for key distribution systems that are currently limited to 200 kilometers via fiber optics. By using this system, satellite-based system, we basically enable secure quantum communications between different countries that are way more far away than 200 kilometers. As I mentioned before, the system could be utilized to secure the governmental and commercial data streams between Europe and Taiwan. And also we can imagine equipping a future EU and Taiwanese platforms, satellite platforms, with secure optical communication modules to increase their security. So this is all from me. Thank you very much. And if you have any questions, I would be happy to answer.
Ladies and gentlemen, let's thank Dr. Krzysztof Marek again for his talk. And would you mind staying for 2 more minutes with us and to see if we have any questions from the audience? Do we have any questions before we let Dr. Marek go? Any questions? All right. Apparently, Dr. Marek, you've given us a very comprehensive and very complete talk. Thank you again. Let's hear it one more time for Dr. Marek. Thank you.
Thank you very much.
Okay, ladies and gentlemen.